Hello everyone, in this video we will cover the section 3.1. In this section we will see a method for second order linear differential equations with constant coefficients. Especially in the chapter 3 we will deal with the methods for solving second order differential equations. Linear equations of second order are of crucial importance in the study of differential equations for two main reasons. The first is that the linear equations have a rich theoretical structure that underlies a number of systematic methods of solution. We can construct many mathematical theoretical structure for second order linear differential equations. This is the first main reason to deal with linear equations of second order. Further, a substantial portion of this structure and these methods are understandable at a fairly elementary mathematical level. In order to present the key ideas in the simplest possible context, we describe them in this chapter for second order equations. Another reason to study second order linear equations is that they are vital to any serious investigation of the classical areas of mathematical physics. There are many applications that use the second order linear differential equations like fluid mechanics, heat conduction, wave motion, or electromagnetic phenomena without finding it necessary to solve second order linear differential equations. We will discuss some applications at the end of this chapter. Okay. A second order ordinary differential equation has the form generally the second derivative of the dependent variable y is equal to the function f, which can be considered as a function of three variables. If you remember the previous chapter, a general form of first order ordinary differential equation has the form, if you remember, y prime is equal to f of ty. We eliminate the derivative of the variable y into one side of the equation, and the other terms will be written in the other side. Similarly, to write a general form for second order ordinary differential equation, we will eliminate the second derivative of the dependent variable with respect to the independent variable, which is the highest derivative in the differential equation. Therefore, we say it is a second order ordinary differential equation. And we will eliminate the higher derivative of the dependent variable in the equation, which is the second derivative, you see, and then we write the other terms into the other side of the equation, which means we will have the independent variable, dependent variable, and the first derivative of the dependent variable, since we have second order differential equation. Therefore, we will have actually three variables except the second derivative of the dependent variable y, which means we can say on the right side of the equality we have a function of three variables, which are t, y, and the first derivative of the variable y. This is the general form of second order ordinary differential equation. In this chapter, we will study second order linear equations of the form the second derivative plus p of t times y prime plus q of ty is equal to g of t. Here you see we have three functions of t. If you remember the previous chapter, the linear equation of first order differential equation has the form, if you remember, y prime plus p of t y is equal to g of t. We have two functions of t for the first order linear differential equation, but here we have second order linear differential equation, which means we will have three functions, you see. Okay, a second order linear equation is said to be homogeneous differential equation if the term g of t, namely the right hand side of the equation, is 0 for all values of t. Otherwise, the equation is called non-homogeneous. In this section, we will focus on second order constant coefficient homogeneous equations, namely instead of functions p, q, and g, we will have numbers. G of t is 0, namely we will have second order constant coefficient homogeneous linear differential equations. How can we find the solution of this differential equation? This is a special case of the general form written here. Instead of the functions, we have numbers. Okay, we have constant functions actually. In this section, we will deal with the method for solving this special second order linear differential equation. So we suppose that y is equal to e to the power r times t, where r is a parameter to be determined, namely we will find the variable r. Then it follows that the first derivative will be r times e to the power r times t, and the second derivative will be r squared e to the power r times t. By substituting these expressions in the equation written here, we obtain namely a times r squared times e to the power r times t plus b times the first derivative is equal to r e to the power rt plus c times e to the power rt is equal to 0. By taking a parenthesis of e to the power rt here, we obtain this one. Namely, from here we have a times r squared plus from here we have b times r plus this one becomes c. And we know e to the power r times t cannot be 0, which means the parenthesis will be equal to 0, you see. Now we try to find a general solution for this differential equation. So this equation is called the characteristic equation for the differential equation written here. Its significance lies in the fact that if r is a root of the polynomial equation, the characteristic equation, then the function exponential rt is a solution of the differential equation. This is the method for solving this differential equation. Okay, we need to find the value of r by using this polynomial equation. For example, let's find a solution for the differential equation written here. You see we have constant for every coefficient of the dependent variable, and the right hand side of this differential equation is 0, which means it is a homogeneous second order linear differential equation with constant coefficients. So we have two solutions for this differential equation, because if we find the characteristic equation from here, so here a is equal to 1, b is equal to 3, c is equal to 2, which means we can write r squared plus 3r plus 2 is equal to 0. So from here, by finding the factors of this term, we find r plus 2, r plus 1. It is equal to 0. From here we obtain r is equal to minus 2, r is equal to minus 1. And from here we know the function y is equal to e to the power rt is a solution of the differential equation. Therefore, we can write minus 2 or minus 1 for r, which means we have two solutions. Y is equal to e to the power minus t if we write minus 1 for r, and y is equal to exponential minus 2 times t if we write minus 2 for r. Therefore, we have two solutions for this differential equation. So in order to obtain a general solution for this differential equation, we need to consider superposition principle as follows. Superposition principle says that if y1 and y2 are two solutions of a linear homogeneous differential equation, then we have two solutions for this linear homogeneous differential equation. So the linear combination of them, namely we can write c1 times y1 plus c2 times y2, is also a solution for any values of c1 and c2. So by superposition principle for this example, the general solution can be written as c1 times e to the power minus 2 times t plus c2 times e to the power minus t. This is also a solution for this differential equation, and by superposition principle we say it is a general solution. Okay. By using the superposition principle. For example, find the general solution of the initial value problem. We have second order linear homogeneous differential equation with constant coefficients, and we have initial values for the solution and the derivative of this solution. So first we need to find special solutions. So we can write second derivative plus 5 times y prime plus 6 is equal to 0, I guess. Yes. So the characteristic equation of this differential equation will be r square. The second derivative corresponds to r square plus 5 times r. R is corresponding to the first derivative plus 6 is equal to 0. So from here we obtain r plus 2 times r plus 3 is equal to 0. So here we have minus 2 and minus 3 for the value of r. Therefore the general solution directly can be written as, by using the superposition principle, c1 times e to the power minus 2 times t plus c2 times e to the power minus 3 times t, because r is equal to minus 2, r is equal to minus 3 from here. And also we have initial values for the solution, namely we know the value of the solution function at 0 is equal to number 2, and the value of the first derivative of the solution of the differential equation is at the number 0 is equal to 3. So first let's use the first one. So we obtain 2 is equal to, for the dependent variable we write 2, and for the parameter t we write 0. Therefore we have c1 plus c2 from here. And also we have initial value for the first derivative. Therefore we need to find first the first derivative of the solution. It is equal to minus 2 times c1 e to the power minus 2 times t, and the second one becomes minus 3 times c2 e to the power minus 3 times t. Therefore writing 0 for the first derivative and 0 for the parameter t and 3 for the first derivative, we obtain 3 is equal to minus 2 times c1 minus 3 times c2. Namely, we have two equations for the constants. Minus 2 times c1 plus minus 3 times C2. Okay. So from here we have, if we multiply the first one by 2, we obtain 4 plus 3 becomes 7 is equal to 2c1 minus 2c1 becomes 0. 2c2 minus 3c2 becomes minus c2. So from here c2 is equal to minus 7. And writing this value into the first equation, we obtain c1 will be 9. Therefore, the general solution can be written as c1 is equal to 9. 9 times e to the power minus 2 times t minus 7 times e to the power 3 times t. Okay, this is the general solution of this second order differential equation with constant coefficient. Also, it is a homogeneous differential equation. Okay, easily we find the solution of this differential equation by using the method. Another example: determine the values of alpha, if any, for which all solutions of the differential equation tend to 0 as t goes to infinity. Okay, we use the same method. The differential equation y, the second derivative, plus 3 minus alpha, the first derivative, and minus 2 times alpha minus 2 times alpha minus 1 y is equal to 0. Okay, yes. So from here we can find easily the characteristic equation. It is r square plus 3 minus alpha r minus 2 times alpha minus 1 is equal to 0. So from here we should find the factors of this polynomial equation. Namely, we should find the roots of this polynomial equation, which are corresponding to the values of r, for finding the general solution. So from here, if you write 2 and minus times alpha minus 1 becomes 1 minus alpha, because we need to find 3 minus alpha when we add them. Okay, the addition of these factors should be equal to the middle coefficient, and the multiplication of them should be this one. So when we find the factors of this term, like this one, so we obtain the last term when we multiply them, and we obtain the middle term when we add them. Therefore, we can write r plus 2 times r plus r minus 1 minus alpha, r plus from here let's consider again so actually we have 1 minus alpha becomes alpha minus 1. When we multiply them we obtain this one, when we add them we obtain this one. Therefore we can write this is true, sorry, this is true. R plus 2 times r plus 1 minus alpha is equal to 0. Therefore the general solution will be c1 times e to the power minus 2 times t plus c2 times e to the power alpha minus 1. Alpha minus 1 times t. Okay. So the question says that for find the values of alpha such that all solutions tend to 0 as t goes to infinity. When we look at the first term, namely we will find the limit of this solution, general solution, as t approaches infinity. Okay. So when we look at the first term, and it should be 0 according to the question. When we look at the first term, when we write infinity for t, since we have minus here, so we will have 1 over infinity, which is equal to 0. Therefore, to get 0, the second term also should be approaching the number 0 when we write infinity for the parameter t, which means the coefficient, the constant, should be a negative value in order to obtain 1 over infinity for the second term. So to get negative value for the coefficient, for the constant alpha minus 1, so alpha should be less than 1. Okay. For all values of alpha less than 1, we get 0 for the limit of this term as t goes to infinity, which means we find, namely, if alpha is less than 1, then both terms will approach 0 as t goes to infinity. Okay, this is the answer of the question. Thank you very much.